Last time we completed the description of the deuteron wave function using the z-axis or radial component of the electron in the deuteron pseudopotential. In this video we will describe the electron wave functions orthogonal to the radial z-axis, the x and y axes. Recall that we described the electron position relative to the deuterons with the electron z-axis always passing through the deuterons. We used a Taylor expansion for the electron position, which presumes the electron stays near the z-axis. We do this to provide a quadratic potential away from the z-axis. This allows for a straightforward mathematical treatment. The quadratic potential allows separation of the wave functions of the electron in the three dimensions and the use of the well-studied harmonic oscillator path integral. Recall that we started with Feynman's integral wave equation, leaving the electron x and y components in the path integral form, shown here for the electron wave function in the x dimension. Previously, we developed the action for the path integral in the form of a harmonic oscillator, as shown, between time a and time b. We can define time a as 0 and rewrite as shown, between 0 and tb minus ta. And note that there is a natural frequency. Now, presume we can express tb minus ta as the natural period times some integer n. We can then rewrite the integral as a series of integrals of the natural period as shown. Since each integral is the same, we can write n times just one of these integrals without error. Now the action in the harmonic oscillator form has a factor n to be carried through. Feynman has derived the kernel for the harmonic oscillator, as shown. This, of course, is a standard set of wave functions for the quantum harmonic oscillator. The difference is the factor n, which comes from the time interval of the action. Recall again that this time interval will be determined by the orbital time of the deuterons. The constant in the exponential of the spatial wave function can be manipulated as shown to give a more intuitive notion of how the factor n alters the wave function. N equal to 1 gives the standard solution. As n gets large, it lowers the average energy proportionately. If you use the previous kernel in Feynman's integral wave equation, we find the wave function as shown, with the as defined before. Now recall the definition of tau, the natural period, as tb minus ta divided by n. We know that E sub n just equals the ground state times small n plus 1/2. If we plug these into the time-dependent phase factor and let n sub n equal n0, the ground state, n, times n small n plus 1/2, we get a constant energy, making all the energy levels degenerate. I know this sounds confusing, but when understood in the path integral formulation, it is very intuitive. So now we have the x dimension wave function with a full set of energy levels, which are now degenerate, but without a value of n still indeterminate. Let us use small n, which will be less than the cap end, and recall the overall wave equation derived from the path integral wave equation, as shown here. And now recall from the z-axis electron analysis the energy versus deuteron separation curve. The z-axis energy had a sort of energy of formation of minus 11,500 electron volts, analogous to the ionization energy of hydrogen. This energy is a constant and is the sum of the electron kinetic and potential energies of the x and y dimensions. We are now ready to calculate n, which will be a function of the deuteron separation. The n-adjusted Ex plus Ey is a straightforward square root function of the force constant at z, derived from the Taylor expansion. If we choose a deuteron separation, say R0, the unadjusted xy energy will look something like this along the z-axis through the deuterons. Previously, we found the z-axis electron wave function, and squaring gives the probability along the z-axis, which looks something like this. Multiplying the xy energy times the probability and integrating over all z will give the unadjusted xy energy. Dividing this energy by 11,500 electron volts will give the value of n as a function of the deuteron separation. Now we can calculate the xy wave functions as a function of z for a given deuteron separation. We could use any of the degenerate energy states to draw a probability plot in the xz plane. For convenience, we'll use the ground state as shown here for a separation of 0.12 angstroms. We can zero in on the electron distribution around one deuteron to see more detail as shown here in a 100 Fermi by 100 Fermi plot. The next slide shows the same distribution from a top view. We can then easily plot the electron probability in the xz plane as the two deuterons approach to a reaction range of 5 Fermi. Shown here is a 100 Fermi square plot from the side, and then the same plot from the top, and last, looking along the z-axis. As we will show in a later video, it's not hard to see how the Coulomb force can easily couple to the electron held so closely to the nuclei. We are not finished analyzing the xy wave function since this one-electron analysis does not give a stationary time-independent state. The time-dependent phase factor is a function of time and energy. The time is a constant fixed by the deuteron orbital time, but the xy energy is a continuous function of z. This will give different phase factors for the electron along the z-axis, which will not result in a stationary state. So next time we will show how the conduction band electrons facilitate a stationary state for the x and y wave functions.